Today, I'm going to show you how I built this motor controller using PWM.
That's awesome. Look at this. Oh!
If you just want to see the circuit, skip to this time. But if you're ready to go on a learning journey where I break down everything about waveforms, duty cycle, and 555 timers, then keep watching. Starting with waveforms. What are they? Well, they are visual representations of either voltage or current over a certain amount of time. In electronics, we use a tool called the oscilloscope, or oscope for short, and its job is to measure either of these values and spit them out on the screen. This allows you to see how a circuit is behaving internally. As a side note, there are multiple waveform types. Most common are square, sine, triangle, and complex. Each has their own specific use, but I'm going to be focusing on a square wave, since square waves only have two states, high and low, and are perfect for PWM. But before I can create the square wave, I need to explain key parts of a waveform to you. There are four main parts of a waveform. The first is the amplitude, which is the maximum amount of current or voltage. Second is the cycle. It's the repetition of the waveform. And third is the period, which is the time of a cycle. And finally, the frequency. It's the amount of cycles in the second. The last three are interlinked via this equation. Frequency equals 1 divided by t. In English, this equation says that frequency is how many times one cycle happens in a certain amount of time. So, how can you find out the frequency of a waveform on your oscope? Well, if you have a fancy one like me, it will do the math for you. But if not, then all you need to do is count the amount of cycles in one box, also called a division. And pay attention to the period, which is labeled sec.div. For an example, if it says 500 milliseconds, then it means each box is half a second. So if you have 5 cycles every 500 milliseconds, your frequency is 10 Hertz. Why is frequency important when it comes to controlling a motor? Frequency depends on the type and size of a motor, but a general rule is if the frequency is too low, the motor will buzz. If it's whining, it will work, but not efficiently. If the motor is running smoothly, that's a good frequency. But too high of a frequency, some circuit components, per se MOSFET or some sort of transistor, can't switch fast enough. That results in unnecessary heat. So that makes your circuit inefficient. So how does a square wave control a motor speed? Frequency alone can't control a motor speed. Frequency allows for smooth power delivery. A thing called duty cycle controls the speed of a motor. Simplistically speaking, duty cycle, I'm having too much fun, is the percentage of how long a square wave is in the on position. This means if my supply voltage to the motor is 10 volts, but I am running at 50% duty cycle, the motor sees the voltage coming in as 5 volts. Or if I'm using a 10 volt supply at 25% duty cycle, 25% of 10 volts is 2.5 volts. So, the motor will spin a lot slower, if not at all, depending on what its startup voltage is. So how can you make a motor controller? Firstly, you'll need a bunch of parts, so just pause the video if you're going on a shopping spree, or go down below into the description. Anywho, the first part of the circuit is a 555 timer. With this IC chip, you can create square waves to control a motor. The IC chip has 3 common configurations. The first one is monostable. It uses one input to drive the output into a high. If the input is low or isn't available, the output automatically resets to low. Bistable uses 2 inputs to drive it. Think of it as a latch reset configuration. And finally, astable, or astable, I don't know how people say it. It doesn't need any external inputs to drive it, which is why I'm using these configurations to generate square waves, because it'll do it on its own. This is the schematic for the astable 555 timer. The 2 resistors will be replaced by 2 100K potentiometers. So I can show you how those 2 resistors affect the waveform. Now, if you notice, when I turn R1, it affects only high time, but when I turn R2, it only affects low time. How is R1 and R2 affecting the waveform? Well, R1 and R2 affect charging time of the capacitor, which affects the high time. And since R2 is the only resistor in control of discharging, this means it will control both on time and off time, while R1 only controls on time, or high time. This of course affects the duty cycle, which in turn also affects the frequency, because on time plus off time equals period. What I just explained is summarized by this math right here. Time high equals 0.693 times R1 plus R2 times C. The C is the capacitor. And time low is 0.693 times R2 times C. Oh yeah, the math to the duty cycle is duty cycle in percentage equals time on divided by time on plus time off times 100. Once I plug in the equations, I get 0.693 times R1 plus R2 times C divided by
0.693 times R1 plus R2 times C plus 0.693 times R2 plus times C times 100.
That is too complicated and will waste so much time if you're doing this on the calculator. So what you will need to do is factor out 0.693 and C. That gets you duty cycle equals R1 plus R2 divided by R1 plus R2 times 100. The denominator can be simplified into R1 plus 2 times R2. Now, if you're not a math whiz, let's put these equations to work. In the first example, R1 and R2 are both 1K ohms. The high time will equal 1.386 milliseconds. The load time will be 0.693 milliseconds. This gives you a frequency of 481 Hertz and the duty cycle of 66.7%. In the second example, R2 will be greater than R1, so let's increase R2 to 3K. High time now will equal 2.772 milliseconds and load time will equal 2.079 milliseconds. This gives you a frequency of 206 Hertz and a duty cycle of 57.1. In the final example, R2 is lower than R1. So, let's decrease R2 to 100 ohms. This will give you a high time of 0.7623 milliseconds, and the load time will be 0.0693 milliseconds. This gives you a frequency of 1202 Hertz or 1.2 kHz and a duty cycle of 91%. Seeing these math equations, you can see their correlation to each other. The higher the resistance on R2, the lower the duty cycle and the frequency. And the lower the resistance on R2, the higher the frequency and the higher the duty cycle. In this circuit, you will never be able to control frequency or the duty cycle alone. Also, you won't get below 50% duty cycle. That's due to the way the circuit's arranged. But let's say I want to control the duty cycle below 50%, or maybe I just want to keep my frequency the same and only change the duty cycle. Well, this guy on YouTube, Skinny R&D, shows exactly how to do that. Essentially, what he's doing is keeping the frequency the same by holding the period length and changing the intersecting point of the high time and low time with this circuit. His video will be in the description if you want to learn more about how the circuit works. Go show him love, because this video would take a lot longer if I had to figure out how to make this on my own. So, yeah. But now that I've filled your mind full of a shit ton of information, let's get into the amplification part. For this section, I will use an N-channel MOSFET. You can achieve this with an NPN transistor, but you might run into some issues with higher frequencies, since most BJTs aren't designed for fast switching, rather they're made for current amplification, while MOSFETs are designed to handle high switching speeds. This is the wiring. Now you might ask why the MOSFET is between negative and load rather than positive and load. N-channel MOSFETs or NPN BJTs work properly when using low side switching, while P-channel MOSFETs and PNP BJTs work properly in high side switching. This is due to the way they are designed internally, and I would need to make a separate video explaining this because it's a lot more complex and I myself don't fully understand it. I just know that it works that way. Now that you've reached the end, you either watch the whole video like a true legend or just skip through it. And if you skipped, how dare you? Anyway, here's me building the circuit. And here's the final video of the motor speed being affected by a PWM wave from a 555 timer.